Hello everyone. In this video I'm going to be doing the first reverse engineering challenge for this channel. This challenge comes from crackme.one, which is a website that I discovered recently. It contains a lot of interesting little reverse engineering crackme type challenges where basically you're given the binary and there's some password or string hidden inside or obfuscated inside of the crackme binary that basically solves the challenge. So this is similar to the reverse engineering challenges in typical CTFs in many respects. So let's go ahead and get started. So the format of this crackme challenge password login is a C++ binary. It is a Linux binary, and it is level 1, which on this site, which ranks binaries between 1 and 5, 1 is the easiest type of challenge. So I figured this would be a good way to start doing these reverses for the channel. So the description for this challenge is it's a simple crackme, there's no patching, just figure out the password. And to follow along, you can just download this challenge here. It will give you a zip file that you can extract. Using the password crackme.one, which is exactly this URL here. So when you do that, you will end up with this binary without these files are actually going to be the IDA files, which of course we're going to be using to figure out what's going on. So there are a couple of ways you can do this challenge. No matter how you do it, you're going to have to look at the disassembly sometime or another. In this case, whether or not you solve it completely statically or you kind of look at the disassembly and go and run the binary in GDB and breakpoint and look at your memory, the two are relatively similar, are going to give you a similar solving times. So let's go ahead and just look at what's going on first. So this is the main procedure. You should get this when you first open this binary up in IDA. And what we see immediately is that it looks pretty complicated. The procedure names are really long. But if you take a closer look at the procedure names, you see that they all start with this _Z, which indicates that this is a C++ compiled binary. And to confirm this, you can kind of look at the automatic comments that IDA provides for this. For these subroutine calls. For example, this first one here, you can see that it is from the std, the standard C++ library, and you can see it's a C++11 standard library. And we can see a lot of these procedures that are called have to do with strings. Okay, so let's take a look around and see what we can find. So the first thing that happens is it looks like we are prompted with enter the password, and indeed this subroutine here basically takes this string and outputs it to the standard out file stream. Okay, after this we have some other stuff that's happening, but what we're interested in is this part here, where we can see that there is a call to get line, which basically gets the line from the standard in file descriptor and puts it into this local variable. So to kind of make this a little bit easier for us, we can go ahead and name this as user input. And that way when we look at it later on, we can see what's happening, although it's not really referenced that much later on. Okay. The next thing that we should look out for is this check password, and actually this is what you should be looking for first. Like, you should immediately try to see what part of this program actually checks the password. So if we look here, the argument to this is a single pointer given in RBP plus var30. var30 is we haven't seen that before, but we can see it is located right here and is the destination argument for this call here, which is the std basic string here, and it looks as if our user input is directly copied into here. And even if you're not sure that that's the case, you can be relatively sure, because if we look into here, this is a standard C++ standard library function, so there's nothing really fancy that's going on with our input there. Nothing is changing there. So, but the important thing is that we look at how our input is checked. So let's go inside this function, and we see from the graph overview here, which is always a good tool, that it looks kind of complicated, but really it's not, because all it is these really long subroutine names. You can see here that this single one here stretches all the way across. But if we take a closer look at what happens, we see that RDI, which is the argument to this function, is placed in this local variable, which we can name user input again. So this is our user input, and okay, so let's go down and see what happens. So the first thing that happens here that's interesting is I see a length check. And the length check is called on this local variable RBP minus hex 40, and this one is referenced here as well. So what is this then? It looks as if RAX, so var40 is the destination in this call here, and it looks kind of similar to what we saw before in main, that function that kind of just copied our user input into RBP minus hex 30. But in this case, the source is this unknown 2005. So if we click there, we can see that this is a string, 3-byte string, DEC. So we can kind of give that a comment there. And so we know that var40 holds this DEC. So just to make this a little bit clear for us in the future, we can just name it buff1, so that whenever this is referenced, we know what's going on. This 1D here passed in RDX, this function, if we look at the comment here, looks like it's just a allocator, some allocator, character allocator thing that is produced up here. So you don't really even have to know what that is at this point. Okay, so let's continue. So so we know that var1d contains this DEC, sorry, not 1d, this buff1 contains DEC, and we saw earlier that linked is called on it. So we know automatically that this here will give 3. EAX will have 3 after the result of this call, because DEC has length 3. Yeah. So this is stored into var1c. So we can just call this length of buff1. Okay, and then here is our user input, which also is called with length. And the result of this is going to be put in RDX. Okay, so this is an RDX. EAX is loaded with RBP plus var18. If we cross-reference that, we see that here we have this FFFF FFF9. Okay, in 32-bit speak, this is a -7. And so if we take that here, So we know that EAX will contain -7. And following this, we have a negation of EAX. So EAX will now contain +7. This CDQE basically converts this EAX into a 64-bit version, keeping the sign consistent. And then what we have is a comparison of RDX and RAX. So remember, RDX was the length of our string. We compare that with 7. And if they are equal, which sets the 0 flag, then AL is set to 1. Otherwise, it's set to 0. And we can see that if AL is 0, in other words, if our length was not 7, then we jump down to here. And it looks like here what happens is R12 is set to 0, and even further down we see R12 is moved to EAX, which is the return value of this subroutine. So in other words, this is bad. We don't want to follow this path here. So we want to make sure our length has, or our input has length 7. Cool, so let's ignore this path now and go on this other path to see what happens next. So it looks like here what we have is another string being allocated and being put into var 60. So it's nothing that we've seen before yet. So let's go ahead and give this another name, buff2. And so this basically allocates a string there and puts that into the address of that into buff2. And then we have a move 0 into var14. Now usually when you see something like this where you have 0 moved into some variable and then a branch after that, usually this variable is going to be some sort of iterator variable. So if we go and look down, and you should look out for instructions like this, we see that var14 is incremented here. So this kind of confirms that, and also you can see that there's a loop, very clear loop that goes around. So indeed, this is some sort of index or iterator, and we'll just call that I for now. So let's look at what happens to this. So after this is moved, we see that we compare I with the length of the buff1, which we saw earlier was 3, right? So if it's equal to or greater, then we go to this part of the program. Otherwise, we go here. So it starts out at 0, so let's look at what happens here. What we have is a move of the length of buff1 into EAX. So in this case, EAX will be 3 the first time we go through this loop. And actually, if we cross-reference this length to buff1, it's not really modified anywhere, so it will always be 3. Yeah, so we don't have to worry about the length this variable changing. So EAX will contain 3. When we subtract 1 from it, we will have that EAX is equal to 2. And then we compare I with EAX. So in the first time we run this, I will be 0. And the following instruction, J and Z, checks if I is equal to 2, right? Because we saw that length buff never changes. We can always just consider it to be 3. 3 minus 1 is 2. So only when I is 2 will this red branch be followed here. In all other cases, we will follow the green path here. So what the green path does is it puts I into EAX and then puts that into EAX here, moves that into RDX, which moves into RSI. And if we look at the subroutine or the procedure here, we see that it's the at method of a string. So if you're unfamiliar with this, we can go here to the C++ reference and look at this public member function string at, and it gives us a description here that it gets the character in the string at the certain position. So going back to here, what we have is that basically what this does is it gives us the character at the position I in the string, which is buff1, and moves that into the AX register, or the EAX register. And we're only worried about the character, so we see that it only uses the low 8 bits, the low byte of that. Moves that into EDX. EDX is moved to ESI, which is the source of this next function here, the destination of which is buff2. So remember what buff2 was, the new buffer that we created. So basically what this does is just copies, if I is not equal to 2, then it will just copy directly into buff2. And we see that this procedure here is just the append. So we just append that onto buff2. Then we increment I and then loop. Okay, so at this point it's pretty clear what happens, right? We know that buff1 contains this weird string DEC. When I is 0, our first character that's copied into our buff2 will be D. Then when I is 1, it will be E. But then after E, so we have D and E right now, the iterable variable I will be 2. And when that happens, when I is equal to 2, we know that that we follow this red path. This red path here looks like it appends some string onto our destination, which is buff2. So everything modifies buff2 here. And so what is appended? It looks like the source is this unknown 2009. So let's check that out. In fact, that's right under the DEC that we saw earlier, and we see that it's K. Okay, so K is appended to our buff2. So if you're keeping track at home, we have so far DE for the first 2, and then when I is 2, it will first append this unknown 2009, which is a K. After that, we have another append here, you can see, right here, and that appends this value at 200, B, which is CAR. Get car. Okay. After that, we still run, we fall through to what would have been run anyways, in which case we take I, which is now 2, the last character of our buff1, which in this case is C, and then we append that onto our buff2. So this is the result of this whole thing going on over here. So it's a lot of work that does very little. Okay, so after that happens, after this whole loop here, it's kind of hard to see it's a loop, but this is a loop right here. After that, we go and take this green path here to this branch. So let's analyze this really quickly. So what happens here is we have, looks like an end and a begin. And again, you can use the reference, C++ reference, to look up these standard public methods, or yeah, public methods. So here we have, if we look up end, or yeah. So end here returns an iterator pointing to the past the end character of the string. Okay. So that will give us kind of the pointer to the end of the string, right? Just like it sounds like. And begin probably gives us a pointer to the beginning. And the string in this case, the RDI, comes from RAX in both cases, which is user input. Okay, so basically our user input is going to be indexed into for the end and the beginning. The end is placed in RBX, which is again used down here for the source. the end is just an RAX, or sorry, the beginning is an RAX for RDI, and then we call this here, which is the standard reverse. Okay, so this is the reverse, and if we go into here, we can see that something is happening, but from the name of it, it just sounds like it's reversing our string. Right, nothing special there. And we can see we can go deeper and deeper and get lost, but into this mess of functions here. But there's really no point in doing that. We'll just assume that it reverses the user input, right? After that, we have the next procedure is an equality check. So if we click here, we can kind of see that this is the equality check. Moves 1 if it's equal to, 0 otherwise. Right, so I'm not even looking at all of what's going on right here. I'm just kind of assuming, based on what's going on, that this is the case. Right, and you kind of want to do this and when you're kind of reversing stuff, because or else it would just take way too long to kind of see what's going on. So it checks equality between what two strings? Let's find out. So RDI is RAX, RAX is user input, and our source is our buff2, right, which was last modified over here in our useless loop over here, right, which produced this. So if our input reverse should give this, then to find our input we should just reverse this. And if we take this and reverse it, starting from the end and reading back, we can see that what we get is just cracked. Right? And if they are equal, then we move 1 into R12D, which we saw earlier, basically determines the fate of EAX. Otherwise, it is going to be 0. 0, let's see, 0 if we move into here, yeah, here. Otherwise, it's skipped over, and we have that EAX is 0. Or, yeah, 1. So in any case, the password here should be cracked, and that makes a lot of sense. So let's go ahead and go into a terminal here and actually run it and see what happens. So what we have here is the crackme program. And enter the password, it is cracked. And we see that the login is successful. Okay, so that is the crackme challenge. Login, password login. It's a very simple challenge. Like I said, you could have run this and seen that there's some buffer 2 being formed here, and then just basically put a breakpoint here and look at what the buffer contains and kind of see, you know, what is all going on here. But because buff2 is so short, in this case it wouldn't really have made much of a difference whether or not you did this statically or partially statically.